His PhD in neuroscience from Weizmann Institute of Science, Israel in 2015. Currently, he is a postdoc researcher at Princeton Neuroscience Institute in Professor Uri Hassan's lab, where he develops tools for improving real-world learning using neuroimaging and computational methods. His research interests include human learning and understanding, brain decoding, machine learning and deep learning, data analysis and signal processing, and semantic technologies. Currently, he is working on a project which involves decoding understanding from student brains, focusing on how students understand and remember new information. In his project, Think Like an Expert, they measure understanding in the student brain and use it to predict and assess learning outcomes in a STEM course. Today, he will talk about the findings from this project. So now I will just play the pre-recorded video, and then sir will sir can take the questions.
Thank you for this kind introduction.
You're most welcome.
Yeah, we can see your screen. You can start. Able to get your audio.
Ayushi, I think you have not shared the audio, system audio. While you are sharing, you will get an option of share the system audio. You just stop sharing and again start sharing.
Yeah, just give me a second. Sorry.
Hello, everyone. Thank you for having me here today. My name is Meir Meshulam. I'm a postdoctoral scholar at the Princeton Neuroscience Institute. My field of study is human learning and understanding. I use brain imaging and machine learning methods to study real-world and online learning. The work that I will present today was performed at the laboratories of Professor Uri Hassan and Ken Norman in collaboration with Mai Nguyen, Liat Hasenfratz, Hannah Hillman, and Yunfei Liu. The title of my talk today is Learning to Think Like an Expert. I'll talk about how a brain represents new concepts and new knowledge, and about what it means for our brains to understand something. I'll also show you what is a good predictor of learning and suggest what we need to do in order to improve our teaching practices so that students learn better. First, I'd like to draw your attention to something that we all know. Teaching is not just about concepts and facts. Teaching actually changes how students think. When I walk into a classroom, or more recently sit in front of my Zoom screen to give an online class, my goal is not just to have students understand the contents of the lesson. It's not just about having the students memorize new facts. For me, as for many teachers, the goal eventually is to change the way students think so that they can ask questions and find answers independently. For us as neuroscientists, this could be thought of as a form of neural engineering. We're trying to change the brains of our students through teaching. This, in fact, is very well known. This idea has been around for a while. For example, in the 60s, Richard Feynman, the famous physicist, observed that the world looks so different after learning science. What he meant by that was that once you've learned a way of thinking about the world, it is there for life. And teachers have known that for a very long time. So here's the outline for what we're going to be talking about today. First, we'll talk about how we measure learning and understanding in the brain in a real-life setting. Then, I'll show you how peers, teachers, and experts can all be a guide to learning success. And finally, I'll show you how this knowledge can help us improve teaching and learning. So the first part of this talk is about measuring learning and understanding in the brain. How do we do that? The main tool that I'm using is functional MRI. This scanner helps us measure neural activity. And what do we use it for? We use it to probe the neural representations of knowledge in the world. The question of how we represent knowledge in the brain is a very fundamental one, and there's a lot of different approaches to look at that. And there's a lot of techniques that have been used. In the last 10 years or so, a set of techniques that have been sort of gathering momentum is techniques from machine learning or brain decoding. What we essentially do is we use computational methods and statistical methods to try and probe what happens in the brain based on what we find with the functional MRI scanner. What we do is we ask people to go in the scanner, and while we're scanning their brain, we show them things from the real world. In our case, what we do is take students and ask them to watch lectures and take exams in the fMRI scanner. Most of the previous work in this field has been done with very well-controlled experiments, meaning that the same stimulus has been shown again and again. For example, if I want to see how the brain represents houses and faces, I'll show my participants a lot of pictures of houses and a lot of pictures of faces. And I'll show the same house again and again and the same face again and again so that I can see how faces are represented as compared to houses. Of course, with learning in the real world, we have to take a slightly different approach. This is how we think about the brain during learning. I want to introduce you to a very simple, a deceptively simple concept. And the concept is about neural alignment between individuals, across individuals. We know today that when people do similar things, their brains are also doing similar things. So, if two people are watching the same movie, their brains will also show similar activity. A very simple idea, right? And it turns out that this idea also works backwards. So we have this idea of neural alignment, where we can see how across individuals, brain activity becomes very similar. And we can use this idea to probe the neural activity in the brains of learners and experts and teachers during learning. In the next part of the talk, I'll tell you how we do that. And spoiler alert, the bottom line is going to be that peers and teachers and experts can all be a guide to learning success. What we did was we used this tool, this neural alignment tool, to examine neural coupling across individuals. We looked at students and teachers and experts during learning, and the hypothesis was that neural coupling during learning will reflect understanding of learned material. In essence, what we think is that the neural activity in teachers' brains and in experts' brains, it reflects understanding of the material in the right way. And so students that are aligned with that will be the students who understand what is going on in the lecture or in the exam. And students that fail to align with the teacher and the experts, those students will not understand what is going on in the lecture. And what we think is that the teacher is actually trying to take the student with them on a journey. They're trying to make their brains behave like the teacher's brains behave, or like the expert's brain would. Let me tell you a little bit about what I mean by that. We ran a study with real students at Princeton University taking an Introduction to Computer Science course. And in this course, we have students watching video lectures. It's an inverted class where students watch video lectures at home, and then they have the exam at the end. What we ask students to do is to watch lectures and take the exam with us in the fMRI scanner so that we can examine their brain activity while they watch the lectures and while they take the exam. We had 24 students and 5 experts. And this, I should say, is a very popular course in Princeton University. This is Introduction to Computer Science in Java, and there is over 400 students in each iteration of the course. Over half of Princeton undergrads end up taking this course. And in our case, our students were asked to watch some of the lectures with us in the scanner. Let me show you a little bit what it looked like to them. So this is Professor Bob Sedgwick from the Computer Science Department at Princeton. He's talking about conditionals and loops. This is one of the first lectures in the course.
With conditionals and loops, we can choreograph the control flow. Before, in the previous lecture, we had what's called a straight line control flow, where we just execute one statement after the other. All our programs were of that form.
So what happens in students' brains as they watch these lecture videos? What happens is that their brain activity becomes aligned. They show the same kind of brain activity, very similar brain activity across students watching the same lecture. And this is what it looks like in the brain. What we're seeing here is that across various regions in the brain, across a lot of the brain, we see very significant alignment between the students and the class. So each student is very much synchronized, very much aligned with the rest of the class. What does this alignment tell us? What can we learn from this alignment across our students? What we see is that the degree of alignment between a student and the rest of the class is predictive of how well that student is going to do in the final exam. What we see is that student to class neural alignment during lectures can actually predict the exam score. What I'm showing you here is neural activity in the hippocampus aligned to the rest of the class. That's on the x-axis here. So the degree of alignment to class. And on the y-axis is the exam score. Each of the blue dots here is a student. And we can line them up and see that the more alignment to class in that student's brain in an area here that is called the hippocampus. The hippocampus is an area of the brain, a region of the brain that is implicated, very important in learning and in memory. So in that region, the more a student is aligned with the class, the better their eventual exam score will be. This is a very important result because it tells us that communication between students is key to their eventual success. The class knows what is right and what is wrong, what is correct and what is incorrect. The class as a whole understands things even if the individual student does not always understand them. So the more a student's brain activity in this brain region that is so critical for learning and memory, the better their neural activity in this region is aligned with their peers, the better their performance would be. So we'll get back to that later. But one important result that falls out of, one important recommendation that falls out of this result is that we can see how important it is for students to work together and communicate with each other, because the class is more than the sum of its parts. Next, we asked what happens with teachers. So I just told you how smart the class as a whole is, but we'd like to believe that the teacher is also smart, right? We'd like to believe that the teacher is taking the class in the right direction. We'd like to examine what happens with this alignment measure between students and teachers. And for this, we actually ran a separate study where we had a teacher in the scanner give a class, and then we had students in the scanner watching that same class. So what we had there, we could compare brain activity in the teacher and in the students and ask, can we use the alignment between teacher and student to predict student performance? And it turned out that yes, we can certainly do that. So what I'm showing you here is that teacher-student neural alignment during lectures also predicted learning outcomes. So the better a student's brain activity was aligned with that of the teacher, the better their understanding of the learned material was. So communication between student and teacher is also very important. And on the brain here, what we see is that significant parts of the brain actually take part in this activity. So what we can do is we can see that brain activity across many regions in the brain gets synchronized between student and teacher. And the better the synchrony, the better the student understands and the better the student performs eventually. Now I'd like to tell you what we found about experts. With the experts, we can sort of be sure that their brain activity is where we aspire, right? So students kind of aspire to have the same sort of brain activity, the same sort of thinking that the experts have on a particular topic, on a particular subject. Students, the way we think of it is that their brains are, or should, during learning, get closer and closer to that of experts, and that students who represent the concept, the student who represent a concept correctly is a student whose brain activity will be best synchronized with that of experts. Can we actually see this in the brain? For this, instead of looking at the lectures, we looked at the exam. Let me tell you a little bit about the exam. This is what the exam looked like. We had 16 questions covering the entire course, and students could see these questions inside the fMRI scanner. They could read them and then give the response verbally. So speak up and respond. And a typical question would look something like this. Are there computational problems that are impossible to write an algorithm to solve? If so, describe one or more of them. If not, explain why. And a typical answer could be something like, the answer is yes. One of the classic examples is called the halting problem, etc., etc. Now we gave them this exam on the final scan and asked them to give us open-ended responses. This was a very hard exam for them. Even at the end of the course, our students only performed around 50% correct. And so we had a lot of variance, which is good for us, so we could see who did better and who did worse. What did we do with this exam? So we examined brain activity during the exam, during each question. And then we could compare brain activity patterns in the students to those in experts. And we could go for each student, we could go question by question and see how similar brain activity patterns in the student were to those of experts. What we find is that student-expert neural alignment was correlated with exam score. So the better the student's brain activity was correlated with that of the expert, the better their response was. So a student giving a response that is wrong, the wrong answer, their brain activity would not be similar to that of experts. But a student giving a response that is similar to what an expert would give, their brain activity was very close to what the experts showed. And this was correct question by question, meaning that we could use this to actually tell what the student understands better and what the student understands less well. For each and every student, we could see what questions were similar to experts and what questions were not. And what I'm showing you here is where in the brain all this happened. And what we see is that it happened in the precuneus and in the anterior cingulate. Those are brain regions that are part of the default mode network. The default mode network is a network of regions in the brain that is associated with self-directed thought and also with memory. So it is very tightly linked to the hippocampus that we discussed earlier. And this network of areas, network of regions, also comes up when we recall information. So the fact that we see this in those regions makes us think that those memory-related networks are where it's important for activity to be aligned with the experts. You need to understand things the same way as the experts and represent them in the brain in those regions that are relevant to memory and learning the way the experts would. Now, the final result that I'd like to share with you has to do with knowledge structures in the brain. What we did here was we looked at how different topics are related to each other in the brain. So in our case, if we have one concept, that is the concept of loops, and another concept, that is the concept of arrays, we wanted to see how the different concepts are related to each other in the student's and in the expert's brain. So we take the brain activity associated with one question and compare it with brain activity associated with other questions. And what this gives us is, for each student and each expert, we get this topic by topic matrix. And this matrix is what we call the knowledge structure. The knowledge structure is how the different concepts learned throughout the course are related to each other. So in this example, we'll expect the concepts of loops and arrays to be very tightly linked. And what we find is that knowledge structures are important, and that knowledge structure alignment between students and experts is also correlated with exam score. So it's not just that having a specific concept in your mind represented like the experts is enough. It's also important to know how the different concepts that you learn throughout the course are linked together. And this knowledge structure alignment is the kind of result that really speaks to how learning changes how we think about the world, how we think about concepts, how representations are not isolated things in our minds, but everything that we learned becomes intertwined with other things that are relevant to it. And if we do that correctly, if we do that like the experts do, then it is an indication that we really understand, and we can see evidence for that in the student's performance in the final exam. So this is what we covered today in terms of the results of our studies. I showed that neural alignment during learning and during the test reflects understanding. I showed how students become aligned with each other and how alignment with the class is a good indication that the student understands something or will perform well in the final exam. How alignment with the teachers is also a good indication that the student understands, and how having the same knowledge structure as the experts is also important for learning and understanding, as we see in performance, in final exam performance. What I'd like to do next is say a few words about how we can use this kind of knowledge to improve teaching and learning. What I'll go through is several immediate takeaways from our studies, but I would like to say that we are still very much actively working on getting more results and more analyses run, and we're hoping to eventually come up with a series of recommendations and suggestions that would be applicable in the real world. I'll cover a little bit of that here and now. So the first recommendations that naturally falls out of the series of studies that I discussed today is to have students collaborate and communicate with each other as much as possible. What we see is that peers are key to success. What I showed you today is that the class as a whole understands the lecture better than any single student, and that thinking like your friends or like the majority of your friends is good for you. It means that you're thinking about things correctly. This is a very important result. It means that we do need our peers. We can't just sit in front of a computer in isolation and try to learn. If you try doing that, you know that it's very difficult indeed. And now we understand why. It's because communication with our peers is very, very important in order to have the right set of representations. It's a tool, and the more we use this tool, the better off we'll be. Another recommendation that falls out of these studies is to identify struggling learners early in the process. And here is something that we found in our studies, that is that we can actually scan the brain very early in the course. So we can scan the brains of students in the second or third week of the semester and already have a good idea of how well they will perform in the final exam. If you think about it, this is actually quite sad. It means that this student could have had a much better score, could have used this learning opportunity much better if they were identified earlier in the course and helped. So if we find those students that are already struggling in the first couple lectures and give them a hand, this could perhaps lead to a situation where these students perform much, much better in the final exam. Early identification of struggling students is very important. The final suggestion that I will make is to focus on the relationships between different topics. We discussed the shared structure, the shared knowledge structure between students and experts. Now that we know how important it is to represent the set of relationships between topics, like the experts do, we can use this to build our classes, to build our lectures in a way that emphasizes these relationships. Instead of just focusing on each subject separately, we should spend time on the entire structure, on the set of relationships between concepts. This is how experts do it, and this is how our students could learn better. So successful learning entails building the right knowledge structure, and we as teachers can help our students get there and build that structure. So here again are the three practical takeaways that I mentioned. First is encourage teamwork. The second is identify strugglers early. And the third is to focus on relationships between concepts. And so with this, I'll end my talk today. This is the end of the recorded talk, but I'm available here for questions and discussion. Thank you.
Mr. Mir, I have a question.
Yes, please.
So one is because the children are coming from different backgrounds, different previous knowledge. So to have the similar kind of neural alignment is a little difficult, I feel. Also, what I understand is that as a student, when I was a student, for example, when the teacher teaches in the class, we all seem to understand, right? So the neural alignment at that point of time in the class would be different than when I sit home, after school and try and read and study things, then my neural alignment will be different, right? So in the class, you seem to understand almost everything what the teacher is, putting forth. But when you sit back and go through the concepts, then is actually you understand whether you've got things right or not. So yeah.
I think it's two excellent points. There is a very big difference between passive learning and actively trying to get things right. So if you're sitting at home trying to get the assignment right, then you need to recall what happened in class. You need to get things right from memory. And this is not the same as sitting in class and saying, yes, I understand what you're telling me. And we see that in our studies. We see that we have neural alignment during lecture for a student. Then when you look at the brain activity during the exam, you maybe you'll find out that they have difficulty in remembering what is how to answer the questions correctly. So yes, this is two very different modes for the brain, I would think. But we also know that they're related, right? We know from our studies that the student that does listen and does get things right in class, they have a better chance of getting things right in the exam in the end. How exactly those things are related, we're still looking into that. One thing that I mentioned in the talk is that what we're interested in more is to have fine-grained measures of understanding. So not just to say this student is doing better than that student, but saying for this student understands loops but does not understand arrays. So let's repeat and let's teach them again about these things that they don't understand that well, so that we can actually help students.
Do you also think repetition is a key to, learning and success? Because there are so many models and, theories which talk about learning and success. So yesterday I was attending one webinar which talked about super memory. So if you have the visuals, they help you retain longer, and that leads to better success in exams and everything. So he was talking about including various visuals. What do you have to say to that?
I think I'll tell you something that I've learned while running the studies. I've learned that our students did not really behave the way that their professors thought they would. So the professor would record a lecture and assume that students are watching lectures in order and only then going to do the assignment and so on. But the students that we examined, they would watch like 5 minutes of the lecture, maybe on their mobile phone on their way to class, and then they would go online and look for that and Google something, and then they would talk to a friend or do something else. So what we see is very dynamic learning. We don't think of learning, we should think of learning as something that happens in class and then the student sits at home and tries to get the assignment right or get the exam right. We should adjust our models to the world where students are actually learning all the time or learning in different ways from different sources. And this is why I think our focus now on class alignment is important, because the student may be doing a lot of different things, but in the end, their goal is to get things right. And this is the same goal for all the students. So in the end, what we'll see is that students get aligned to each other, even if they don't get aligned to some external source.
There are a couple of questions. One is, will it help in integration of different subjects for connection of concepts?
Integration of different subjects, I'm sorry.
So for example, say teaching math in a different way. Ms. Indu Kumari, you can correct me if I'm wrong, or integrating it with some other subject like history or chemistry or something. So that means they're able to make these connections between different topics.
So as I mentioned, making those connections is very important for successful learning. And I could only guess that making connections across fields is beneficial. We're actually running now is a study that I haven't mentioned, but a study that we're running right now is trying to see how different subjects related to each other in the brain. So is it the case that when I take a math course and then a math lecture and then a history lecture. Those things they live in different networks in different regions. They don't interact with each other, or do they have some synergy effect between them? This is something that we're looking into right now.
That's interesting. That also goes back to the discussions we were having yesterday. There's another question. Have you looked at alignment during learning versus recall? That is the test condition for the same concept, and is it and its relationship to performance?
Yes. So this is one thing that we're also looking into right now. We haven't been able to isolate brain activity for a specific concept during learning yet. So if I want to look at brain activity for a specific concept, I could ask you a question about it. And this is what we did during the exam. But if you want to see brain activity for a specific concept during learning, you're going to have to maybe only talk about that one concept. And this is a very natural thing to do. This is not what you usually do in class. Usually you teach a concept and you ground it in other concepts. And then the relevant brain activity becomes, it includes all of that together. So we're, again, this is something that we're doing now. We're developing a method for isolating concepts during the learning process. We started from isolated concepts, and now we are trying to see if that could also help us isolate the concepts during this actual class, during online class, which is what we are most interested in. So online, real life learning instead of isolating specific points, because this is what our students are actually doing.
I think the next question is what you said you would be your next study. That is, do you think these results would be valid in other subjects like literature, history, and the others? So I think that's a study that you just mentioned, if it was the same networks.
Yes, we're looking at different students, but and different classes. So we're a different set of students, a different cohort of students, and looking at different subjects. And then we're trying to see how these things are interfering with each other.
Okay. So the next question, computer languages are very structural and are designed to be unambiguous. So neural alignment in knowledge structures is plausible. Can these results be extrapolated to concepts taught in, say, natural language, which is much more ambiguous?
So the lectures are not in computer language. So the class that we have, it's true, it's about computer science. But as you saw, you could see the lecture, the professor is speaking in natural language. He is trying to make students understand, and this would be difficult if you were only giving them like the math of it. So we think that our results should be applicable to different subjects, but we don't know that yet. And this is one of the reasons that we are running this other study with other subjects.
Yeah, so the next question is, so that there was alignment when the students were inside the fMRI machines. Would the alignment be higher or lower if the students and teachers are actually present together in a classroom? I think this is also to do with the machine itself, right? I mean, it's not a very friendly machine to be inside.
Yes, so definitely lying inside an fMRI scanner is not the best way to get aligned with the rest of the class or with the teacher. And we actually, I feared a little bit that doing that, watching the lectures in the scanner would interfere with alignment. What I think is that if you're out of the scanner, if you're actually in direct interaction with the teacher, with your peers, you'll see much higher alignment. It would not only be limited to what you can see through the scanner, it will also, through the video, it will also include everything that happens in class and happens to everybody together. And so my prediction is that we'll see much higher alignment in actual classes. Of course, this is something that is difficult to prove because we don't have this machine in class.
I think there's another additional question from the same Professor Jayashree Ramdas. So you did draw conclusions about collaborative learning. Do they follow from the results?
The recommendation for students students to communicate with each other is based on how we see that the class as a whole is a good template for good understanding. This is what the recommendation is based on. If we didn't find that, then I couldn't tell you anything about students communicating with each other. I would say students should listen to teacher or something like that. But once we see that the class as a whole is a good template, then it makes sense to recommend for students to talk to their peers as much as possible, to work in groups and teams, and so that we can do what we can to increase that alignment between students, which is beneficial to them.
Somebody called VA wants to ask a methods question. That must be Vinu. I can unmute and ask. Please do so, Vinu.
So my question, I was just trying to understand about, how you try to calculate this measure, and from my minimum understanding of, trying to read up your paper on the side, that you look at time intervals, right? You look at 30-second windows and how the neural alignment is within those windows, and then you average. So now my question is that sometimes the learning might happen. So, it could be that for the past 2 minutes that I'm trying to process things, but then the next 30 seconds, I get it. So my neural alignment would be high just then, but previously it would be low. So if you average across, am I losing that information? So because everyone, assimilates information at different time intervals, maybe. So
This is an excellent question. This is an excellent question. The lab that I'm part of has been developing this method of alignment, looking at alignment and coupling between individuals for a long time. And there is also, apart from the way that I used in this study, there's also ways of looking at alignment through time. So exactly that measure that you're talking about, now alignment is low, but the next moment alignment is high. And there is a study from a few years ago that actually used exactly that to look at how children understand mathematical concepts in Sesame Street videos. So a Sesame Street instructional video would teach them about math concepts, and then you could actually track the individual children and see when they actually are better aligned with the class, and when they get it better. They didn't actually look at the class; they looked at adults. So they would compare children and adults, and they think that where children and adults are synchronized, this is where this is a good indication of the children actually getting it. But yeah, this is a very interesting aspect of it, that understanding is not something that it doesn't happen with me and with you at the time. It doesn't have to happen immediately. It is not linear. It's not 1 or 0. Maybe you're somewhere in between. And these are all things that that are part of our research program for the coming years.
But that can be also, this is Kavita here again, but that can that be estimated from actually a different kind of an analysis that you can do, like a moving window kind of an analysis? Just to see, to just Vinu's question where she asked about, at this time I'm not aligned with you, but it takes me maybe 2 more seconds, 3 more seconds, 4 more seconds to kind of, oh yeah, I get what he's saying. So there's a different method that can be applied to do that.
Yeah, so one way is to really look at the time domain. So we try to see where people understand and where they don't. But maybe what we thought in this study is that maybe this shouldn't be our focus, because we don't really mind it if the student understands something this minute or the next minute or after class. What we care about is whether they got it eventually. And so this is why we focused on what happens in the exam. And in the exam, at the end of the course, you could actually see if the student understands or does not understand, and how that reflects in their brain activity.
Okay, so there's another question. Is there a way to figure out if lack of or poor prior knowledge would be the cause of misalignment with the expert and the rest of the class?
Lack of, sorry?
Prior knowledge, what you knew before.
Yes. So we can only speculate why a student would be better aligned or not. And certainly if you have people from different backgrounds and different prior knowledge, that could affect how they get aligned. In our study, I can't say a lot about that because in our study, students were very homogeneous. So they were all Princeton students taking the same course, and I don't have information, I don't have data about people coming from different backgrounds. But that's a very interesting question, and I think it's very interesting.
Yeah, and then there's a question on because fMRI might generate different patterns for both the expert and the learner. Then how to judge if the learner has learned well? I think that's an answer you gave, that you looked at the final result of their
Yes.
exam, right?
Exactly. We compare how we gave the same exam to the experts and to the students at the end of the class, and then we can see how similar the brain activity for the experts and the student is.
So what the question is about, I think um, using another multimodal technique. I mean, like using an EEG along with your fMRI, then would maybe see this real-time class settings where the responses are fast and the synchronization happens in the temporal frame.
So some of my colleagues, they do exactly that. They take EEG sets and they try and record what happens in students' brains in class. This is more portable, and they can get data from actual people sitting in actual classes. And yes, this is a line of studies that has been very successful.
Yeah, I think some of them are questions on how did you scan people while teaching inside the scanner. I think that it's a paradigm question, the fMRI design paradigm question.
Yeah, so the paradigm here is simple. We have a video of the class, of the lecture, and we have a setup where people in the scanner can watch videos and listen to them. And so we show them the video and record what happens in their brains.
So when you talk about this alignment between the teacher and the student, it's basically the teacher, at this time you're assuming that the teacher is teaching with, it's not that the teacher is also scanned at the same time, isn't it? It's not like both of them are in the scanner.
So a study that I was part of that was led by my colleague, Mai Nguyen, in the lab, that I mentioned in the talk, that's where she actually recorded herself giving a class. So 25, I think, minutes of class, she would speak up, and she had slides and everything, and she scanned herself in the scanner giving this class. And then she could scan students in the scanner while they were listening to the same class. And it turns out that her brain template, her brain activity was a good template for understanding in the students. So a student that during the lecture showed brain activity that was aligned with her could actually give better answers at the end in the final exam that was given.
Okay.
So
That's
everything that I talked about also works with teachers.
Okay. The next one is, I think, one of our students itself. So is the time of the day has any significant effect on alignment, like more number of students getting similar alignment in the morning or the evening?
This is a great question. We've wondered that because we had to scan our students over the weekends. We had 2 scanners at the basement, and we had students coming in at all hours during the weekend because we couldn't ask them to come during the week because of scanner schedule. And some of them were scanned in the morning and some were scanned during the night. And we actually haven't looked at that. We don't know if time of day is important. In recent years, there is more and more indication that time of day matters for all kinds of stuff. in and out of the brain. So it's important for us as human beings, as animals. We haven't analyzed that yet.
Yeah, that would be a very interesting study for, I think, students across the world, about when to have classes and at what time are they more awake. The other question, do the students vary? I mean, does the results change if the student is under any anxiety prior to the scan?
We had students get acclimatized to the scanner, so it wasn't the first time. It wasn't their first time in the scanner. We had them come in, they get familiar with this, with scanning, with the scanner, with the setup, so that when they are scanned for this class, they are comfortable in the scanner. And they all indicated that they stressed and they're comfortable. And those who were stressed did not take part in the study. It makes sense that the reason we did that is that we don't want people lying in the scanner being afraid and stressed. This would definitely affect our results and would definitely affect their learning. Also, we don't want to cause people any stress. So in our case, all our students indicated that they are comfortable with scanning.
Okay, so I'll take the last three questions, which are already in the chat box. One says participants received monetary compensation, so you paid for them time, right? So do you think that the incentive is to pay, the incentive paid help them pay attention more just to please the experimenter? Was there any of those biases?
I couldn't tell you because there's another study you need to run, right? You need to ask if the size of the monetary compensation changes how they listen and how well they do. The good news is that you don't need an fMRI scanner for that, right? So you can just run a study with giving students money and letting them see the lectures and see if that affects their learning. My guess would be that it's not a big deal because the amount of money involved was not huge. It was really just to compensate them for getting up in the morning over the weekend and coming to get scanned with us.
So the next question is, would there be a difference because in the alignment in an elite university like Princeton, would there be a difference?
So if there would be a difference for
difference
students
based on the university. Yeah, Jayashri, go ahead, please.
In an elite university like Princeton, perhaps the difference between students is not that much. Whereas in typical classrooms, you might have more variations in ability. So I mean, elite institute and an elementary course. So all the students would basically be on the same page. Whereas in typical classrooms, you might have more variance in the classroom.
This is a legitimate concern, and again, from our cohort of 20-something Princeton students, it's difficult to draw any meaningful conclusions about more heterogeneous populations. What I can say to that is that not all our students did so well in the final exam. So I mentioned that in the final exam, they did around 50% correct. We had students do around 95% correct, and we had students do around 20% correct. So we did have a range of learners and learning ability, but in terms of heterogeneity of the actual group, we don't have this data. And yes, I think that to be able to draw conclusions about more heterogeneous classes, you'd have to run the analyses, you have to run the studies and come up with good answers. At this stage, we don't have them yet. This is the beginning.
Yeah, I think we should. Professor Jayashri, you have another follow-up question, or?
No, I think that's
Okay.
a nice explanation. Thank you.
Yeah. I think this next question was on the dependence on course, and I think that was covered because that was something that they're going to do now as the next part of their study, look at different other courses. So I think I'd like to thank Mayor for his wonderful talk and also actually answering so many questions from all of us. Thanks a lot. And that's a really good study. We will actually be circulating that paper to the students here. And when you do the other courses, I mean, when you're running for other subjects, we will be looking to the results just to kind of understand how this whole process between teacher and student happens. Thanks a lot on behalf of all the participants. Thank you for the wonderful talk, and have a great day. Thank you.
Thank you for inviting me, and thank you
Thank
for wonderful questions.
Thank you. Thank you. Bye-bye.